How chemical reactions occur and how fast or how slow chemical reactions occur. So we looked at, this has to do with thermodynamics, these two driving forces. And what we looked at were these three factors which determines how fast or slow a reaction occurs. Okay, so temperature, concentration, and catalyst. So note that, okay, so we can draw a reaction energy diagram. So which one represents the fast reaction? This one or that one?
This one.
Yeah, so this one represents the fast reaction because yeah, it has a small activation energy. Which reaction is endothermic?
This one.
So note that, let's see, in this case here, here's our reactants, here's our products. So which one's higher in energy? Yes, the reactants are higher in than the products. Here's our reactants, here's our products. So which one's higher in energy? Reactants. So which one's the endothermic reaction? None of them. Yeah, they're both exothermic. Okay, so we looked at some fast and slow reactions, and then we looked at reaction rate. So in reaction rate, that's the change in concentration of a reactant or product with time. And we also looked at how this graph of concentration versus time looks. We looked at the rate law. So the rate law tells us how a change in concentration affects the rate of the reaction. Now, note again that the rate is directly proportional to concentration in this rate law. The rate constant K is a constant. If we change the temperature, what happens to the rate constant? Does that change or stay the same? Yeah, it changes. If we keep the temperature the same, what happens to the rate constant? It stays the same. Okay, so we talked about how to determine the rate law for a reaction. Okay, so we looked at how to do that, and looked at those two methods. So here's method one. So we did this in lab. So you change the concentration of one reactant, keep the other reactant concentration constant. You do several experiments and measure the rate. Then you can figure out the order of the reaction with respect to each reactant. Then the second method, which is more difficult, is to do one experiment, but you have to figure out a way to measure the concentration at different times in the experiment. Okay, so that's the other way to do it. And then we looked at a few applications of that. Oh, let's see. Here's one on the last part of lab 3 was to determine the activation energy. So we did that by measuring the rate and the rate constant K at different temperatures, then applying the Arrhenius equation. So based on this equation, we plotted the natural log of K versus 1 over T. And the slope of this graph is equal to minus EA over R. So you guys did that in lab. And I know for the 11 o'clock lab, we didn't get to this part, the timing part, but I heard that the 2 o'clock lab did this, and quite a few of you were bragging how close you got to your assigned time. No, you guys aren't bragging. Okay, we'll find out about that. Then we talked about reaction rates. How rate laws are related to the reaction mechanism. Note that in the reaction mechanism, the rate determining step or slowest step is the important step. Then we looked at a few examples on reaction rates. So here's quiz 5, and a related quiz 5 question. And then for lab 3, propose a mechanism for this reaction. So note again that when you propose a mechanism, the rate determining step has to have one IO3 minus and one HSO3 minus in the rate determining step in that reaction mechanism. Okay, then we talked about catalysts last week, and we did an application using hydrogen peroxide. And then let me just show you this before we review quiz 6. So for the hydrogen peroxide decomposition, the activation energy I looked up is 72 kilojoules per mole. When it's catalyzed using this enzyme in your liver, the activation energy drops to 28 kilojoules per mole. So note that there's quite a difference in activation energy. So if you do a calculation comparing the rate constant for the catalyzed reaction versus the uncatalyzed reaction, note that the ratio is 3 times 10 to the 7th or 30 billion. So that tells us that the rate increases by a factor of 30 million by using a catalyst, which is a very large increase in rate. Then I also looked this up, although I didn't do this calculation. It says without enzymes, the peptidase enzymes, which breaks down proteins into amino acids, would take 300 years to digest a steak in your stomach without that enzyme. So I guess you wouldn't go hungry. Although you could work backwards, see if the same factor is involved, then you can figure out, well, if it takes 300 years without the enzyme, how fast does this enzyme work to catalyze this reaction? Okay, so in other words, if it's 300 years uncatalyzed, how fast is this reaction with this catalyzed enzyme? Okay, so you can work backwards to figure out how many minutes or hours or seconds it takes for this enzyme to work to break down proteins into amino acids. Okay, here's some other examples how a catalytic converter car works. What causes a hangover? So this is Tuesday, so I'm hoping that, see if you do that kind of stuff over the weekend, that you do that in moderation so you don't get a hangover. Okay, so. And then we talked about plastics, and then we talked about 2 different types of reaction mechanisms. Okay, let's review quiz 6. In lab 1, you heated ethanol with vinegar in the presence of sulfuric acid to make ethyl acetate. So for each change in reaction condition, determine whether each quantity increases, decreases, stays the same. So if you raise the temperature, what happens to the reaction rate? Does it increase, decrease, or stay the same? Okay, so if you raise the temperature, the rate should increase. We know that because the reactant atoms or molecules are moving faster or slower. They're moving faster, which means that they'll collide with each other with greater energy, which means that there's a more likelihood or higher likelihood that bonds will break or bonds will form. What happens to the rate constant K? Does it increase, decrease, or stay the same? So when you raise the temperature, the rate constant should increase. Okay, so let me write down these 2 formulas. So for 1, here's the rate is defined by the rate law. Okay, so note that the rate is proportional to concentration, but it also depends on K. So K is defined by the Arrhenius equation, so that's equal to A times E to the minus EA over RT. So when T increases, the rate constant K should increase too. And if the rate constant K increases, that tells us that the rate should also increase. Okay. What happens to the activation energy of this reaction when you raise the temperature? So does it increase, decrease, or stay the same? Yeah, it should stay the same. So again, when we look at our energy level diagram, we plot energy versus the progress of reaction. Okay, so if these are our reactants and these are our products, this is our activation energy. So it doesn't matter if we change the temperature, the activation energy should be the same. If you go into the second changing condition, we use diluted vinegar solution. So what does this mean? What are we changing here by using diluted vinegar solution? We're changing the concentration. So if we change the concentration, what happens to the reaction rate? Yes, if we, now when you're using diluted vinegar solution, are you increasing or decreasing the concentration? Yes, so if you're decreasing the concentration, what happens to the rate? It decreases. What happens to the rate constant K? Okay, it should stay the same. Okay, because note that based on this formula here, the rate constant K does not depend on concentration, it depends on temperature. Okay. And what happens to the activation energy when you use diluted vinegar solution? It stays the same. And finally, what if you happen to forget to use that sulfuric acid catalyst? What happens to the reaction rate? Yeah, so the rate should decrease because we know that a catalyst increases the rate, so if you forget to use a catalyst, it should decrease the rate. What happens to the rate constant K? Does it increase or decrease? Or stay the same? Okay, so if you're saying that the rate, decreases because you forget to use the catalyst, what's happening to the rate constant K? It's also going to decrease. Now note that it decreases because what's happening to the activation energy? Okay, so if this is the energy level, reaction energy diagram for the catalyzed reaction, for the uncatalyzed reaction, what's going to happen to the activation energy? It's going to stay the same, increase or decrease? It should increase? Yes. It should increase. Okay, so this is for the uncatalyzed reaction. Okay, so this is the uncatalyzed reaction. And this is for the catalyzed. With the catalyst. So the reaction mechanism change when you change the temperature. Okay, so again, this wasn't on here, but if you had another column here, if you raise the temperature, does the reaction mechanism change? Okay, so again, if you raise the temperature, does that change the reaction mechanism? That is, those sequence of steps by which bonds break or form. Nope. Okay, so it's not going to change. Okay, so note again, you raise the temperature, rate constant is the same. Rate constant increases, the activation energy stays the same, but the mechanism is going to be the same too. Okay? If you lower the concentration, is that going to change the mechanism of the reaction? Okay, so by lowering the concentration, does that change the sequence in which bonds break and bonds form? Nope. So, again, note that changing the temperature or changing the concentration does not change the reaction mechanism. If you forget to add the catalyst, does that change the reaction mechanism?
Yes.
Okay, so let me go back. Let me go back to this slide here. So note that this is the decomposition of hydrogen peroxide. Here is the mechanism using the I- catalyst. Okay, so here's the mechanism. Without the catalyst, here is the mechanism. Are these two mechanisms the same or are they different? Yeah, they're different. So if you use a catalyst, what does that do to the reaction mechanism? Yeah, it changes the reaction mechanism. So maybe I've got too much type. I got too much text on this slide here. Just need to put one sentence on the slide. The catalyst changes the reaction mechanism, and just leave it at that. Okay. And then I think we talked about this already. Which change in reaction condition changes the reaction mechanism And we said that that's going to be the catalyst. Okay, so let's just spend a few minutes introducing chemical equilibrium, and then we'll spend the last part of lecture doing some, reviewing some problems, sample problems for your exam. Okay, so most of the reactions that we've looked at so far in Chem 1 and Chem 1B are reactions that go in one direction only, the forward direction. Turns out that there are many reactions that go in the forward and the reverse direction. So, for example, we looked at this type of reaction. The reactants react to form product. In other words, you have A plus B going to C plus D. But it turns out that those products can react together to reform the reactants. So C plus D can form A plus B. So in this reversible or equilibrium reaction, both reactants and products are present. Now, since this is a chemistry class, in most sciences we want to quantify these observations. We can quantify how much reactants and products are present by looking at an equilibrium constant. So this equilibrium constant is given this symbol capital K. So note that lowercase k is rate constant, capital K is equilibrium constant. So that's equal to the product of the concentrations of products divided by the product of the concentration